All right. All right. So good job to everybody who presented today. Andy is going to clean all this mess up later. And hopefully I won't trip over. I was playing around with that. Stuff's pretty cool. Like bang your hands into it and whatever. All right. So so here's what we're going to do. Because you guys did the presentations, we won't quite get through 2 full chapters today. So I kind of fast forwarded a bit through the first chapter on ocean waves and things. But because this topic came up earlier in the year, I thought we would take a couple minutes and talk about tides and why tides actually happen. Because a lot of people don't know why tides happen. Okay? I'm going to show you a couple videos on that as well. But before we get to the videos, I'll just show you a couple pictures here. What's going on? Notice, okay, this is the Earth, even though it doesn't look like the Earth. This is the Earth, okay, and the Earth goes around like this, okay, and actually goes like this, I guess, in this direction. No, I guess this way. And the moon, okay, pulls on the Earth, but it also pulls on all the water around the Earth, okay? And the moon's gravity is pretty big, okay, and so when it pulls on the water, what happens is you get this bulging effect on both sides, actually, of the planet. So what happens is the water gets pulled a little bit here, and it makes the videos that I'll show you describe it a little bit better. But what it does is it pulls on both sides. Okay, it actually pulls a little more on this side than on this side, and the water bulges up so that on this side, if you can see the moon up here, okay, you're at a high tide. Okay, if you were perpendicular up here to where the moon is, it would be a low tide. If you were on the opposite side, it would also be a high tide. And then down here, it's another low tide. Okay, and then as it goes around, as it turns around, the closer you are to, well, I guess it's kind of a weird picture because it's going this way. But well, I'll show you the videos in a second. We also have to take into consideration the sun, and we also have to take into consideration, when the sun is like this relative to the, say, the moon up here, and the sun here, or the moon down here and the sun here. There's not 2 moons, although it looks like that. Or when it's like this as well. Okay, so the alignment of the sun. Okay, so let me show you these videos, if I can find them here. Will the North and South Pole ever have a high tide? Good question. They do have tides up there. Yes, in fact, I think they're pretty big in the Atlantic Ocean portion of it. But they do. It just depends on the tilt of the Earth and where the moon is in relation to the bulging part of it. So they do have tides. Let me see. Hang on. Okay. Okay. So we'll do this one first, and then we'll do the one by our favorite Professor Dr. Hewitt. Okay.
Can you believe that? Your time is amazing.
All right, hold on. Okay. Okay. Can you hit the lights over there and hit the lights over there?
How do the tides work? Here's Adam Hart-Davis with a biscuit, a pickled onion, and an orange.
Tides are a complicated business. Let me show you what I mean. Imagine that this chocolate biscuit is the Earth, and this pink blob is me on Moses' side, sitting on the edge of it, and spinning round and round, getting night and day. Now, let me bring in the sea. In a simple world, the sea would just be a sphere, even depth all the way around. But of course, the world isn't simple, and the main influence on this sea is the pickled onion, or the moon. And when it's here, what it does is to pull up the water towards itself, and it pulls up the Earth a bit, so you get a hump of high water on either side of the Earth. So as the Earth turns, I get high tide, low tide, high tide, low tide. Now, the sun also has an influence. Here is the sun, the orange, and when it's over here, what it does is to diminish the effect of the moon. It only pulls about half as hard because it's 400 times further away. So it lowers the...
Not quite true. It actually pulls about 200 times harder than the moon, but it pulls because it's farther away, it pulls less hard on one side than on the other, because it's farther away and the distance matters in that case. But the overall pull is harder. It's just the difference between the pull on one side or the other. So I think you got that just a little bit wrong there.
Side. On the other hand, when it's in line with the moon over here, then the pull is in the same direction as the moon, and you get super high tides and super low tides, and they're called spring tides. And you get those whether the sun is on the same side as the moon or on the opposite side. Now, if that was all there was to it, predicting the tides wouldn't be too difficult. But in fact, there are further cycles you have to think about. For one thing, the sun is higher in the sky in summer than it is in the winter. For another thing, the moon's orbit is not a circle, but an ellipse, just like this plate, in fact. So sometimes it's further away from the Earth than at others. And there's even one cycle of the sun and the moon that happens only once every 18.61 years.
He doesn't describe what that
How
one is.
was it for you?
Okay.
Please comment on and rate this movie.
Okay. Let's look at the one that I think Paul Hewitt probably does it a little bit better. You don't actually see him, but you hear him.
I didn't get the British there.
You didn't get the what? You didn't understand it? Okay, a biscuit's a cookie, yeah. All right, so.
For centuries, people have wondered about the role of the moon on ocean tides. Here's the moon in empty space. Not quite so empty, for in its vicinity, let's suppose there's a giant blob of water. For the moment, we'll assume both are at rest. If no external forces act on the giant blob, it's pulled inward by both surface tension and its own gravity to take the shape of a sphere, the shape having the least surface area. But there are external forces on the water. The moon exerts gravitational forces on the blob and forces that are not uniform. Since the force of gravity between two bodies varies as the inverse square of their separation distance, the moon pulls harder on the parts of water closer to the moon than in parts farther away. If the body of water is closer to the moon, the elongation is more pronounced. Not only are the forces greater, more importantly, the difference in forces between the closest and farthest parts is greater. Opposite sides of the blob seem to be stretched apart. Let's move the water back a bit and put planet Earth in the middle of it. And let the planet spin, say, one rotation each day. Looking down on the North Pole and watching Earth rotate, an observer at the seashore notices that the water is deep here, a high tide. Oh, notice the water is becoming less deep. And here we're at low tide, the best time to dig clams at the beach. Then the water begins deepening again, and before you know it, we have another high tide. The cycle continues. This computer animation makes this clearer. Nearer the moon, we see a greater stretch. Put a solid body inside the blob, move it out a bit, and here we see a North Pole view of Earth rotating daily beneath the ocean bulges. So with each rotation of Earth, we get 2 high tides and 2 low tides. So we see how Earth is elongated by the difference in lunar poles on it. The elongation is on opposite sides of Earth, so it doesn't make sense to think that the elongation is only on the side of Earth that faces the moon. A corresponding elongation occurs on the moon as well, even though it's solid. Consider the elongated moon, as I'm drawing, very much exaggerated to help me explain an age-old question. Why does only one side of the moon face us? The moon, like all bodies that rotate, rotates about its center of mass, shown by this purple dot. Here's a situation where the center of mass and center of gravity don't coincide. Because one side of the moon is closer to the Earth than the other, the close side is more gravitationally tugged toward Earth than the farther away side. This results in Moon's center of gravity being somewhat closer to Earth than its center of mass. I draw this with the red dot. And a purple dot for Earth's center of mass. This red vector from the moon's center of gravity is the gravitational force that Earth exerts on the moon. The moon's long axis, through both its centers of mass and gravity, is shown by this white dashed line. The result is a torque about the moon's center of mass, which tends to rotate the long axis of the moon into alignment with Earth's gravitational field. We see the same behavior with a compass needle that aligns with a magnetic field. Once aligned, the torque no longer exists. The alignment of moon's long axis continues as the moon circles Earth. We say the moon is tidal locked to Earth. How about that? Now, getting back to ocean tides. It so happens that the sun also plays a role in ocean tides. Because of its vast distance from Earth, the difference in its poles on near and far sides of Earth are much less than moon's difference in poles. Although less than half as effective as the moon in raising tides, sun's influence is there because it's so massive. Most noticed when the sun, moon, and Earth are aligned. Here we see the moon in its new moon position. Tidal influences of sun and moon coincide when this alignment occurs, producing extra high high tides and 6 hours later, extra low low tides. At times when the alignment is perfect, so the moon casts a shadow on Earth, we have a solar eclipse. But that's another story. These greater than average tides are called spring tides, although they have nothing to do with the spring season. Spring tides occur at or near the time of a new or a full moon. When the moon is not in line with the sun, when it's positioned 90 degrees to the line between sun and Earth, tides due to the moon and sun partly cancel each other. That occurs when an observer on Earth sees a half moon in the sky. How do you think tides are affected at this time of month? Did you say smaller high and low tides then? If so, you're correct. These tides are called neap tides.
N-E-A-P.
Our treatment of tides is simplified. Average high tides are only a meter or so above the average surface of the ocean. So the bulges we depict are greatly exaggerated. And why the tidal bulges don't line exactly with the moon or sun, why they don't occur at the same time each day, and why variations in tides occur in different parts of the world, these all make up another story, a fascinating one. I leave you with a conservation of water type question. Suppose you go to the beach to dig clams at the time of an extra low tide. Is it reasonable to assume that in about 6 hours, the high tide that follows will be extra high? Think about that. Until next time, good energy.
All right, what did you think about that one? Did you get it? Did you understand it? Check the lights. What's that? Oh, that's neat. This is called a neap tide. N-E-A-P. Neap. He did sound a bit old. You know, he's actually in his 70s now. No, sorry, 80s, I think. He's still eccentric. He's still eccentric. I think he's retired now. I think he's retired. I think he lives in Florida. Actually. Okay. So, all right. So the tides. Okay, when we have the tide on this side, is this going to produce extra large and small tides, or like kind of medium tides? Extra large tides, more dramatic. And then here, not as high. Yeah, medium ones, neap tides. Okay. All right.
Now, how come all the water doesn't go to one side?
How come all the water? You know how much water that is?
Yeah, but
All the water doesn't go to one side.
If the moon and the sun are on one side,
Sure.
and it's oval, why is it oval like that? Why is the water oval like that?
Well, do you know how much water would have to move?
Yeah.
Like trillions and trillions and trillions and trillions and trillions of gallons of water. You can't. It just wouldn't move. It maybe if like the Earth stopped moving.
By all the water, but I mean like.
it's a fair amount. I mean, you know, the tides go up and down. You know, in certain parts in the world, the tides are like 40 feet, like in Maine, like really big tides. So you get a fair amount of movement of the water, but remember, 6 hours later, you're going to be the opposite side. So.
Can you explain that as the surface tension of the water? It's trying to pull everything to the center.
Well, that's yeah. I mean, the good point. It's not really the surface tension of the water. It's the gravitational pull of the Earth is still pulling on the water. I mean, a lot, right? So there's that too. Okay. All right. Let's spend a little bit of time talking about the atmosphere, which is kind of cool. Okay. By the way, this is the last chapter on Earth science. Next week we actually do astronomy. Woohoo! Okay. Sorry, a couple people will miss it, but you guys will be home, so we'll all be jealous.
Space math.
Okay. All right. So we've talked a little bit about some of the details here. In our atmosphere, okay, the most prominent gas is nitrogen. 78% of the air is nitrogen. A lot, right? 21% is oxygen, and then the rest kind of falls out. Argon is not even a percent. Neon, et cetera, et cetera. There's some hydrogen. There's some methane. Water vapor. Let's see, between 0 and 4%. We'll get to why that's the case in a little bit. Carbon dioxide, not much. Ozone, tiny little amount. Okay, this is actually the average value in polluted air, I guess. Okay, CO2 is increasing, by the way, probably because of all the cars that we drive around, right? And there's some dust and some other things in there. Okay, so if we look at the atmosphere, Earth's atmosphere, and this is like going from the surface of the Earth up, right? The atmosphere has a number of different layers. Okay, we've got the troposphere, which is this layer that we're all in right now. Okay, and planes fly in the troposphere, and we breathe there, and so forth. Okay, and that's up to about 14 kilometers or so, which is what, about 14 kilometers is about, yeah, it's about what? About 8 miles or so, something like that. Yeah, from here to Somalia. Well, that's straight up, though, right? Straight up. Okay. Then you get the tropopause, which we're not really going to talk about, which is kind of this layer between the troposphere and the stratosphere. Then you get the stratosphere. Okay, that's where the ozone layer is, way up there. Okay, it's pretty far up. Then we're talking like almost 50 kilometers up, troposphere. Then you get the mesosphere, next one up, which goes up to about 90 kilometers. Okay, and then above that you get the you get this thing called the thermosphere, which is kind of in here, which we will talk about, but it's not in the diagram. Then you get the ionosphere, okay, up to about 350 kilometers. Okay, and then after that, it's not really the. I mean, there's very, very diffuse gases, but that's the exosphere. Okay. By the way, the space shuttle is in here. Okay, space shuttle is still technically in our atmosphere now. Obviously, it's way too thin to think about breathing or anything, but there's still particles up there. Okay. All right. Let's talk a little bit about each one. Troposphere, the lowest one, lowest, thinnest. Okay. 90% of the atmosphere. So you go above the troposphere, you're not going to be breathing. Okay, just there you go. Weather happens in the troposphere, and we'll get to weather in a little bit. And the temperature decreases as you get higher. And we talked about this before, I think, about 6 degrees Celsius every kilometer you go up. Okay, 6 degrees Celsius per kilometer. Okay, and let's see. Planes fly at what? 30,000 feet? I don't know how many kilometers that is. About 5 miles, maybe? What's that? 4 miles? Yeah, something like that. So, go ahead. It's actually much cooler up there, but I'll talk about that in a minute.
The Red Bull guy?
Yes. Oh, when the guy jumped out of the thing. He was still in the troposphere as far as I know. Right? I don't think the balloon got up that high. I don't think a balloon can go outside the troposphere. I just don't think it's possible for that to happen. Yeah, 16 kilometers. Yeah, I don't know. Anybody remember how far he fell? Like something like 8 miles or something. I forget.
I can't remember.
I can't remember either. We'll have to look it up.
That happened when we were in South Carolina. We watched it.
Oh yeah?
Yeah.
Oh, okay. Top of the troposphere, negative 50 degrees Celsius. negative 50 degrees Celsius, right? That's pretty cold. Right? When you're flying in the plane, it can be like negative 30 degrees Celsius, right? Which is pretty cold to begin with. Okay, after the troposphere, you get the stratosphere. Okay, this is 50 kilometers above the surface. Let's see. So 16 kilometers. Oh, you know what? We got that tropopause in there, I think, too. Oh, no, sorry. The top is 50 kilometers, so 16 to 50. This is where the ozone happens. Ozone, remember, absorbs that harmful UV. And the temperature actually goes up in the troposphere, the stratosphere, because you're getting that absorption of UV radiation, and therefore it's causing the particles that are there to go a lot faster, and therefore it heats back up to about 0 degrees at the top. Interesting. Okay. Then we have the mesosphere. I'm not going to make you memorize these, by the way. We have the mesosphere. Okay. It goes to about 80 kilometers. The mesosphere temperature goes back down again. So we've got a lowering of temperature, then an increased temperature, then a lowering of temperature again. Okay. You don't get much absorption of UV, and it goes down to about negative 90 degrees Celsius. We're getting really cold up there at this point. But then we have the thermosphere. Then temperature starts going up and up and up and up. Turns out there's not much atmosphere at all up there. And therefore, each little particle of gas doesn't have much to bump into once it gets going. So they go really, really, really fast, and temperatures get up to about 1,500 degrees Celsius, which is really hot, right? So if you're trying to go through the thermosphere, it's really hot up there, but take a look at this. There's not much gas, so you don't actually feel that temperature. Like, it would feel really, really cold still. But if you actually measured the average kinetic energy of the molecules, they'd be really fast. There's just not that many molecules there, so it doesn't feel very hot if you were to like stick your hand out of the space shuttle as you were going up or something crazy like that. Okay? All right, we get that. It's kind of similar. An analogy is when we had the balloon that was like 50,000 volts, right? Or the sparkler that was like 1,000 degrees. Each little sparkle is 1,000 degrees, but all together, not many little pieces, so it wouldn't really burn you so much.
Mine is blown.
Okay? Yeah. Mine is blown. All right, thermosphere. Okay, then we have the ionosphere. The ionosphere has what in it? Ions, right? It's electrified, basically. Okay, and this is where you get the auroras. Anybody ever seen any auroras? If you ever lived in Alaska or lived in, I don't know, like Northern Europe or something, if you look out, it's beautiful. Yeah, you can see all these crazy like colors in the sky, and that's because the Northern Lights, yeah, Northern Lights, and it's because of the magnetic poles and the charged particles, and they glow. So it's pretty cool. Okay, all right, the exosphere is kind of where space and the atmosphere kind of taper off together. Like space starts, the atmosphere is ending. Okay? After about 500 kilometers, you're going to get escaping of particles. If a particle gets up that high, it's probably going to be able to escape the Earth's gravity.
You said that's where the space shuttle is?
No, the space shuttle is actually in the...
That's the thermosphere, right?
Nope, it is in the mesosphere. What did we say? Yeah, the mesosphere, I think. Nope, sorry. This is up to 90 kilometers. It's in the ionosphere is where the space shuttle is. Yeah, so good. All right, good. So we talked a little bit about the temperature here. And take a look at this graph. This is a cool graph. This is the temperature going this way. Okay, temperature's going this way, and this is height above the Earth. So notice, as we go up in the troposphere, colder, 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 colder. Right? But then we get into the stratosphere, stays about the same for a while, and then gets warmer, 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 warmer. What's going on here? Why is it getting warmer? Absorbing UV here. Gets into the mesosphere, colder, 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 and then gets into the thermosphere, and then, whoa, gets really, really, really hot, up to about 1,500 degrees. And then the exosphere, it kind of like tapers off. Now, out in the middle of space, what's the temperature? It's tough to decide because are there any particles out there? There's some, but not much, right? It's pretty much a vacuum. In a vacuum, if there's no particles, you can't really define temperature. So, tough to do. But that's the weird zigzag pattern about the temperature as you go up, 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 and away. Okay. All right. We've talked a little bit about this before. Solar energy. Okay, solar radiation, electromagnetic radiation from the sun. It's just light. Okay, we've got visible and short wavelength radiation, which is stuff you see, of course. And then you've got the radiation that's like IR, infrared radiation, that's re-emitted from the Earth's surface. You can actually get some actual light re-emitted too, like if you're standing on the moon and you look down and you see the Earth. Well, that means that light has bounced off the Earth from the sun and come back up, right? But you do also get the infrared and longer wavelength. Okay? So how does the atmosphere get warm? Well, a couple ways. Yes, light rays from the sun actually go into the atmosphere and warm it up a little bit. But really what's going on is the sun warms the ground, and then the ground re-radiates, and that's what warms up the Earth. Heat rises. Well, warmer air will actually start to rise. Why? Any idea?
Because it's lighter.
It's kind of like, well, kind of because it's lighter.
Density?
Yeah, it's dense. It's less dense, so therefore it's got less mass, and it's getting buoyed up by the other air, right? Kind of like what Tyler was talking about in his little presentation earlier. Okay. All right. Obviously, Earth's temperature varies according to the degree of solar intensity. Like if you live in a place like 11 degrees north, like where we live, right? This is the reason we call 11 degrees north 11 degrees north. Is because we're at the 11 degree latitude line, right? Or wait, latitude, latitude line, right? Okay. So we can do that when you get, obviously, get higher temperature, more solar intensity. Okay. How about this? Here's kind of where we are in Djibouti, right? The sun is pretty much straight up, straight on most of the year, because we're not too far from the equator here, okay? When it's at its highest point, okay? 90 degrees straight up and down. You get lots of light right in that little area. When you're at an angle, in other words, if it's wintertime or if you're farther north, you get an angle to the sun, and guess what? Not as much light actually hits each little individual part. Okay? Or at higher latitudes. Well, yeah, higher up. Okay? So we're here, which is why we have Black Flag days all the time. Although I think they mess it up. I can't figure the flag thing out. So when I wake up, if I go running at like 5 in the morning, it's really hot and humid out, but it's still a green flag or no flag. It's just because they don't do it at night, or they don't update it at night? Oh.
Yeah, not till 8.
Not till 8 in the morning? Oh.
Yeah, and then all of a sudden, black flag.
And all of a sudden it's black flag. Although I've seen yellow flags in the middle of the day. So,
You know why? Yeah, we're there. What club is?
yeah, the wet club's right out here.
Yeah, during the day,
Yeah.
like sometimes it would be a shadow.
And that's when they read it?
Yeah.
That's
They
a little
read it
silly.
every-
They should not read it in a shadow.
Half hour.
Yeah. All right. OK. So again, the variation in solar intensity is what causes our seasons, basically. You guys know about the equinoxes and the solstices? Well, this is what's happening. The Earth, which is tilted on its side, as it goes around the sun, how long does it take to go around the sun?
A year.
A year, exactly. Okay? And as it goes around the sun, okay, when it gets to, let's start here. When it's angled like this, the northern hemisphere is getting straight on. Okay? It's getting more straight on anyway. And it's summer up here. And by the way, if you're at the North Pole during the summer, there are a certain amount of days where it's light the whole time. Right? Yeah. Actually, is it half the year light the whole time? Then half the, no, it's not exactly. It doesn't just flip off. It's kind of, some parts of the year it's full-time light. Okay, right around June 21 or 22. Halfway or a quarter of the way through the year later, okay, notice now the sun is basically hitting both hemispheres as it goes around at the same angle, right? And it's now springtime in the, let's see, it is springtime in the northern hemisphere and and autumn in the southern hemisphere. It goes around December. Well, now we're tilted the other way. So now the angle of the sun to the northern hemisphere is at less of an angle, and so it's winter. Okay? And then the exact same, then we kind of reverse the process as we go along to the autumnal equinox, where it's again 50-50. Okay? We spin which direction? Well, around the sun. Depends which way you're looking at it. I mean, if you're looking below this way, it's going this way, right? You think it's this way? It doesn't go summer to. Oh, sorry, I did go the wrong way. Yes, sorry. Summer, then fall, then winter, then spring. Yeah. So sorry, did go the other. You were right. That's an extra point for you. The what else? Oh, by the way, when is the sun farther away from the Earth? It changes by about 1 million miles. It's about 93 million on average, but on one side or the other, it's about 94 million. On the other side, it's about 92 million. No, 93.5. So here, closer or farther away?
Closer.
Nope. It's actually farther away in summer for us. In Australia, it's a little closer, right? Because, or sorry, it makes a little difference. It doesn't make much of a difference, though, because we're 93 million or 92 million miles away. That amount of sun is not going to make much of a difference. 1/92 of this is not going to make. Okay. All right. Okay. Okay. We kind of went through this. When the suns are closest perpendicular, that's when you get summer. When you get an angle, then you're in winter, and you get fall and spring in the middle, obviously. Okay. All right. So now let's do this. Let's talk a little bit about air motion around the Earth. In other words, wind, really. Okay? Why do we get wind? The basic underlying reason we get air motion around the Earth is because parts of the Earth are heated at different amounts. Okay? So like you said that like hotter air will tend to rise up. Well, cooler air and hotter air causes a pressure differential, and then the air moves between those two pressure differentials. That's really the biggest thing here. Okay, we've already talked about this. The atmosphere, and Tyler talked a little bit about this too. The atmosphere pushes down on the Earth. Okay, total weight of the air above you. Okay, the higher up you are, fewer air molecules, less pressure, because there's not as much air pushing down on you. Okay, we got that. Now, there's this thing called the temperature-pressure relationship. Okay? There's this convection cycle which comes from that. Meaning, like Louis was saying, a parcel of warm air. Let's say this was your warm air. Okay? It's going to rise through the atmosphere, be buoyed up. The cooler air is going to actually sink down. Okay? And it's all because the warm air is less dense than the cooler air. Okay? Convection currents in the air actually stir up the wind, and the wind goes from higher pressure to lower pressure, sideways basically. Okay? Wind is sideways, not up and down generally. Okay? And the more this pressure difference we have, the stronger the wind. Okay? So it's all about pressure differences. Okay. And we said this earlier, we get uneven heating of the Earth's surface. Local differences contribute to local winds. So if, for instance, you are, let's say, well, Djibouti is a bad example because there's not that many trees. But if you're in one area where there's a lot of trees and the ground below is not getting as warmed up, okay, but then nearby there's like kind of asphalt or a deserty kind of area, well, you're going to get different amounts of warming up of those two different areas. That's going to cause this pressure difference, which is when you're going to get some wind flowing through. Okay? So we also get planet scale differences because of the solar intensity, which we've already talked about, due between like the equator areas and anything between, and then the North Pole. Okay? And then you get and these planet scale differences are what causes global wind patterns, like prevailing winds. Like if you happen to be on the west coast of the United States, the wind generally comes off the ocean onto shore. Okay? And that's kind of nice because it's normally a little bit warmer, and it's, keeps you moderated. a little bit. Unless you have a cold front. Yeah, we'll talk about fronts in a minute. OK, ready? Check question. What drives air from high pressure to low pressure? Convection currents, wind, the pressure, gradient force, or water vapor.
Convection currents.
Convection currents are what drives air from areas high pressure, low pressure? Wind is your final answer? How about the pressure gradient? OK, it's the difference in pressure that makes the wind go from one side to the other. Because it's kind of like, it's like a, well, I mean, when you have a vacuum, right, that causes a pressure difference on one side of the vacuum on the other, and then that's what causes the air to flow. OK, so in this case, the pressure difference, not the wind that causes the flow. It's the pressure difference that causes it. OK, so we're still talking about temperature, pressure. So warm air expands. OK, and warm air has a lower density and a lower pressure than cool air. Cool air contracts, and cool air has a higher density and therefore a higher pressure. OK, keep those in your brain for a minute. OK, well, we already kind of went over this a little bit. Local winds, same thing because of not the surface heating. Land and water. Land heats and cools more rapidly than water, so therefore you get uneven heating and cooling. So I guess here we do get some uneven heating and cooling. It was nice, the wind today. It was still hot out, but lots of nice wind. Okay? And remember, wind flows horizontally, higher pressure to lower pressure. Okay? Of course, the Earth's rotation. How long does it take to rotate once?
5 days.
24 hours. How long is it? 24 hours to rotate once around, right? That's a day. When the Earth rotates, right, and the Earth revolves around the sun and rotates on its axis, okay? Yeah, the Earth's rotation greatly affects the path of moving air. Anybody ever heard of this, the Coriolis force? Okay, Coriolis effect, if you want to call it that. Moving bodies deflect to the right in the northern hemisphere and to the left in the southern hemisphere. Now, you might have also heard that the reason when you flush your toilet, the water goes one way or the other has to do with the Coriolis effect. That's not. Coriolis effect is a big effect on big pieces of air in the Earth, not your tiny little toilet, right? You did that in South America, yeah. It kind of depends on the way your toilet's built and how hard you flush and all that kind of stuff. You can get it to go one way or the other depending on, yeah. And a lot of times they have inside, when it shoots water out, it shoots it along the side in one direction. So that's why it does so. Sorry to burst a bubble there, but I know. On The Simpsons, I know. Where they go to Australia and they have this giant machine. Oh, prank call. Oh, that's funny. It also depends on the deflection of the wind depends on the speed of the wind and the latitude. So if you're going faster, you're going to get more deflection. And you get more deflection up at the poles than at the equator. Tends to be more wind the farther north you go, in many cases. Anybody ever sailed through the equator? Anybody a shellback here?
Well, on a ship.
Shellback, there you go. On a ship? Well, on a ship. At the equator. I'm a golden shellback, by the way. You know what a golden shellback means?
That's how you meet up.
You meet at the equator and the international date line. Pretty cool. Anyway, do you remember at the equator what the winds were like? You remember at the equator what the winds were like?
No, I was too busy.
You're too busy? Generally, at the equator, it's what's called the doldrums, which is where there's not much wind at all. And it partially has to do with this fact that there's where you're at the equator and there's not this much wind deflection down there. And in fact, people who actually sail on sailboats through the equator have to take that into consideration. Sometimes it can take a long time to get through the equator because you might not get much wind.
I got pictures of the line.
Pictures of the line? Is it a big log? White? Yeah. All right. So again, pressure gradient. I don't know why they keep repeating this, but the Coriolis effect, apparent deflection of the wind because of the rotation, and when the air is near the ground, it does have some frictional effects as well. So that'll slow it down a little bit. Okay. All right. Here we go. Global circulation of the atmosphere. Unequal heating of the surface and the Earth's rotation. And if you look, okay, here's the doldrums, equatorial low doldrums. Okay, down here, the wind, southeast wind, trade winds down in the southern hemisphere. Okay, a little farther down, you actually get westerlies going the other way, and it's kind of the opposite in the northern hemisphere. Westerlies are what we generally get in, like in California, for instance. Okay, all right. The prevailing westerly winds are affected by the Coriolis effect by the deflection of winds. To the right in the northern hemisphere and the left in the southern hemisphere? We have one vote for that, maybe. To the left in the northern hemisphere and the right in the southern hemisphere? Laterally towards the poles or westward? To the right in the northern hemisphere? There you go. Good job. Okay. To the right in the northern hemisphere. Westerly winds means it blows from the west to the east. I always get that mixed up. I won't forget it now, though. But I generally mix that up. If it's a westerly wind, it means you look west and the wind hits you in your face. Okay. That's a good way to remember it. Ah, now I'll never forget. We'll see. Whoops. Okay. Let's talk about how the ocean circulates now. Okay. First, we talked about the atmosphere, how it circulates. Now let's talk about how the ocean circulates. Okay. Ocean currents are just streams of water that actually move. Anybody ever gotten caught in an ocean current? You guys ever see Finding Nemo? Right? There's that like scene where they're going along with the turtles, and they're in that like ocean current under that like some sort of what do they call it? Not the jet stream. What's the one I'm thinking of? The yeah, it's one of the currents. I forget what it's called. I forget what it's called. The one that's in Australia, yeah, of course, because that's where they are. Right. So the atmosphere we know has lots of layers. Well, guess what? The ocean has lots of layers as well. Okay, we've got this deep, deep zone, transition zone, and then a surface zone. Okay, and the layers of the ocean will actually be affected by the currents are affected by the layers that you're in as well. Okay. First, we have surface currents. Well, most surface currents come just from wind, believe it or not. Okay. The more wind, that's kind of the direction the currents are going to generally go. Okay? So the prevailing winds tend to give you the direction of the currents. We also have this thing called Ekman transport. You do not have to memorize that. But there is the Coriolis effect, which does affect large bodies of water, like oceans, causes water currents to actually deflect according to where, as opposed to where they should be going based on the wind. Okay, it's called Ekman transport, or the Ekman force. Okay. So right here, if the wind is going this way, well, the waves kind of go this way, or maybe a little bit even this way because of the Coriolis effect. Okay. All right. We also have, well, we've already said wind is the strongest factor on surface currents, but you also get the Coriolis effect. We've got these currents that are actually kind of twisting. We call those gyres, okay? And they rotate counterclockwise and clockwise depending on which hemisphere you're in, northern hemisphere or southern hemisphere. There we go. There's some gyres. What's that?
They be called eddies?
They could be called eddies, although eddies is generally in the air, I think. But in the water, we got gyres. I'm not sure. Maybe they are called eddies. Yeah. We call them that. Yeah. Okay. All right. These gyres actually cause heat transport from the equatorial region to the latitudes because they go and they transfer a lot of that heat up there. Okay? The Gulf Stream, that's what I was thinking of before. The Gulf Stream carries lots of warm water from the tropics into the higher latitudes. So if you happen to be like England and you get the Gulf Stream going right past England, right, you tend to be relatively warm. England is at the same latitude as like Canada. Right? But Canada gets hammered by snow. England stays kind of relatively warm. Doesn't really get much snow in the winter. Okay. All right. Anybody ever heard of El Nino or La Nina? Okay. Yeah. So El Nino is a global water circulation pattern. Okay. And when you don't get that many trade winds that are not that strong, okay, we call this an El Nino year. Okay? And what happens is it changes like the pattern of the currents here and completely can change the weather on both sides of the Pacific Ocean. Okay? You can get lots of different changes because of that. And you get different types of weather based on the winds. So it's actually a big effect. Okay, that was surface currents. Deep water currents. Okay, not driven by wind. There's no water or no wind down in deep water, but they are influenced by gravity. Okay, when you get in the poles, the water freezes. Okay, and when salt water freezes, okay, it's not the salty part is not what's freezing. It's just the water itself. Okay, the salt actually comes out of solution. So when you get in the poles, you get the fresh water, basically ice that forms, and you get saltier. The rest of the water becomes saltier because there's more salt per liquid water. Okay, cold salty water sinks to the bottom. Okay, because it's more dense. Okay, the sinking water pushes deeper water out of the way, causing the bottom water to flow outward. Okay, and then you do get some mixing there. Okay, and the deep waters slowly kind of back up. So deep under the ocean, you do get these currents, and it's caused by gravity, basically because you've got different salinities of water. Okay, and this is called the conveyor belt process, which can take lots and lots of years.
Lots of years to equalize, or lots of years to get a gram of salt from?
I think lots of years, to bring the deep waters back up to the surface. So there is this kind of churning, but it takes a long time. Okay. All right. Let's take another break, and then we'll finish up Earth science. Thank you. All right. So let's finish up the last chapter on Earth science, which is the weather. Okay. We're going to talk a little bit about weather. Again, this is not my specialty, but we will go through this, and we'll talk all about the cool things that happen because of weather. No pun intended, I guess. And then we'll talk about at the end. We'll talk about some violent weather. Okay, we'll get to there. All right, four factors influence the weather. Atmospheric moisture, which kind of makes sense. Okay, if there's moisture in the air, we can get rain, and we can get dew, and we can get all that kind of stuff, frost. Obviously, temperature influences the weather. Air pressure. What measures air pressure? Barometer measures air pressure. Okay, and where you are in the Earth, like in other words, the arrangement of the land and water features. Okay, 4 things that influence the weather. Okay, all right. Let's start out with moisture. Okay, humidity. We don't know anything about humidity here in Djibouti, but humidity is the mass of water vapor in a certain volume of air. Okay, relative humidity is just this ratio: the amount of water vapor in the air divided by the amount of water vapor air can hold at that temperature. Okay, question: go down to Antarctica. Is it very dry down there or very humid?
Dry.
We have one vote for dry. Lots of ice down there. Going with humid.
Is it considered the biggest desert in the world?
It is considered the biggest desert in the world, I think. It's very, very dry at Djibouti as well. Is Djibouti a desert or more? I don't know what it is.
It's more of a hell.
It's more of a, yeah, good point. No, but it's very dry down there. As temperature goes down, the ability for air to hold water goes way down. Okay, so this is one of the reasons that you have nice dry air in wintertime in cold areas, because the air just can't hold much water. It's also why you scruff your feet across the carpet and get those big shocks, because the air is very dry and you don't get much leakage of the static electricity off your body. Anyway, this is the relative humidity, amount of water vapor divided by the amount of water vapor the air can hold at that temperature, okay, which we can measure. Now, air that has as much water vapor as it can possibly hold, it's just like a solution that has as much of the solute that it can possibly hold. What do we call that?
Saturated.
Saturated. Okay. Air that contains as much water vapor as it can is saturated. Warm air holds more. Cool air holds less water vapor. Saturation can occur when you just drop the temperature. So let's say it's really humid and really hot out, and a cold front comes in and cools all that air down. What's it probably going to do? Probably going to rain on you, because the water's got to come out of the air somehow, because it can't still be held in the air. It just comes out as precipitation. Okay? Saturation and condensation are more likely in cold air, okay, because you have slower moving molecules. Okay? If you're moving fast, you can actually collide, and it's easier to evaporate. Okay? If you're going slow, you just kind of like these guys, they just like kiss. Right? They don't actually like bounce off each other. All right. Okay. So how much, what is the saturation vapor pressure here? If you're at 0 degrees Celsius, the vapor pressure is 6.1, not very much. If you're up at 35 degrees or 95, you can hold lots and lots of water vapor. Okay, which is one of the reasons that here in Djibouti, Eric, you with us? Here in Djibouti, we have nice humid air because we are hot and we're right next to the ocean. So all that air, all that water can evaporate and go right into the air. Okay, that's part of it. Okay, other places that are similar, Florida, right? California, not so much. I think California, I'm not exactly sure. I don't think, well, it's not as warm, for one, generally, but.
It also depends on what part of California.
Yeah, that's true. If you're in Los Angeles, it's pretty humid. Well, Bakersfield is isn't it very dry in Bakersfield? Dry, but this is not near the ocean at that point. Bakersfield is not near the ocean. Yeah, but it's not right near the ocean. Okay.
Yeah, Japan is humid.
Japan, very humid. Okay, near the ocean. Okay, so the evaporation rate obviously depends on the temperature. The higher the temperature, the faster those molecules can bounce off each other, more evaporation. Condensation rate doesn't, though. It doesn't matter how hot you are. The condensation rate only depends on how humid it actually is. Okay? When the evaporation rate is greater than the condensation rate, well, you're not going to have 100% humidity, meaning it's saturated, because you're evaporating out more of that. The relative humidity is always less than 100%. Okay? Because you're not going to need to, you're not going to condense down and condense out that water vapor. Okay? Anybody ever hear of the dew point?
Yes.
Dew point. That's when saturation occurs. Okay? When you reach the dew point, water vapor actually you get condensation. Okay? Which is, we know on like the grass, is dew. Okay? Why does this happen? Well, like at night, let's say during the day, it's nice and warm, and you get a lot of water in there, and then at night it cools down. Well, you can't keep that much water in there. It has to kind of condense. That's why you get the dew on the ground. Okay? High up in the air, when you condense water, what do you get? Clouds. Okay, you get clouds. Okay? And what do you get down when you get condensation near the ground? Fog or dew or frost. Okay? You're mist. Yeah. So the difference between a cloud and fog, just the height. That's it. Yep. Okay. All right. The more dense the air, in other words, the lower altitude you are, okay, the more molecular collisions, and the air pressure is higher. Air pressure, density, and temperature all related to each other. Okay? We have this thing called an adiabatic process. Now, we didn't talk about this when we talked about heat transfer and thermodynamics, although we could have. An adiabatic process is when air actually expands or contracts. You with us, Andy? Yes. You're not looking over here. You're looking over there. Okay. When air expands and contracts but doesn't transfer heat, we call that an adiabatic process. Just a vocabulary word, right? When expand, now, what you can get though, this will probably be on the next slide, what you can get if you don't transfer any heat, but you expand, okay, you actually cool way down. Okay? If you contract and you don't transfer any heat, you still can get a temperature increase because now if their molecules are expanded, right, they may not, they won't bounce into each other as much, so therefore they'll be going a little slower. Okay? We have this thing called the ideal gas law, which says the following. The pressure equals the density of the air, in other words, how thick the air is, if you will, times temperature. Okay? Now, when you combine that with this adiabatic expansion, look what happens. Okay? The temperature of a dry parcel of air, okay, decreases as you go up. Now, we already talked about the temperature does. We already talked about this when we talked about the atmosphere. And all you guys said, oh, that's great, of course. Well, here's why. As you go up, okay, the air actually expands. And as it expands, the temperature goes down because of that expansion. Okay? That's actually called the dry adiabatic lapse rate. In other words, how fast it cools depending on the temperature. So if you're at the ground and you're 25 degrees Celsius, well, you go 1 kilometer up, 10 degrees Celsius less temperature. Then to 5, then -5, -15, and you're only at 4 kilometers up. This is why when you're flying along in your aircraft, okay, it's really cold outside that window. Like it's -30 degrees or something outside the window. It's because you've gone up high enough that the air has expanded and cooled down that much. Pretty cool. Okay. By the way, when they take the air from outside the airplane and pump it into the airplane, you know how big the heaters are that have to heat that air up? They're actually air conditioners. They're not heaters. Compressing all that air to make it such that it's the pressure inside the aircraft that you want warms it up so much they have to actually put it through an air conditioner to cool it down enough so that you don't burn up. The actual act of compressing it back again. OK. All right. A couple things about weather. There's interesting things. There's about 1 billion of these things we could talk about. But a couple that the book mentions. There's these things called Chinooks. OK? Like the salmon, a Chinook salmon. OK? Here's what happens. So you've got a little mountain here. OK? Warm, moist air. Let's say the ocean's over here, and it's nice and warm, and the moist air comes up here and starts going up this mountain. The wind kind of carries it up the mountain. Well, what do we know happens as it goes up? What happens to it? Expands and gets cool. Well, if it's moist and it's cool and it can't hold all that water anymore, it starts to rain. Okay? So it's cooled down, and you get lots of clouds and lots of rain on this side of the mountain. Well, as it goes back down, it warms up. But guess what? It's not really that moist anymore. It's lost a lot of that. It's lost a lot of that moisture because of the rain. It comes down here, and it's nice and dry. Okay? And this side of the mountain doesn't get much rain. In fact, it stays nice and dry the whole time because of the fact that you get this rain happening here because of this cooling and as the temperature is up. So they're called Chinook winds on this side of a mountain. They don't always happen, but they can happen.
On that side of the mountain where the Chinook wind is, you get more vegetation, or it's going to be more like?
It's going to be drier, so you may not have much vegetation because it might never rain over there. So you might not have much vegetation at all. This side you're going to have some vegetation. Yeah, this side maybe not. But it might be nice to live if you don't like rain. Depends. Dry over here. Okay. All right. If rising air actually stays warmer than the surrounding air, it'll continue going up. But as it goes up, it gets cooler, cooler, cooler. So eventually, it'll stop rising, right? If it's continually rising, like it's nice and warm and it starts rising, as it expands, it doesn't cool as fast as the air around it, it'll keep rising. We call that unstable air. Okay? Eventually, you get to that point where it does match the surrounding air. And when the temperatures match, you don't expand anymore, and you don't rise anymore, so it becomes stable. Okay? So it's kind of this, goes up, and then eventually gets to a point where it's the same temperature, and it does not rise anymore.
Is that what causes turbulence in
Is that what causes turbulence? I'm not sure exactly what causes turbulence in an airplane. I think it does have to do with the pressure differences as you're going through. I think the pressure differences.
The thermal's pushing up.
Thermal's pushing up, and yeah. Okay.
That's why going into Vegas is always entertaining.
Oh, because there's lots of thermals.
Oh my God,
Yeah.
it's ridiculous.
Yeah. Well, a lot of.
It's always fun seeing people for the first stop fly get there.
Oh, really? It's pretty bad. I've only flown it a couple times. It hasn't been too bad, but sometimes you actually get what's called a temperature inversion. Okay? Temperature inversion is when you're actually warmer above and cooler below. Okay? And in that case, none of the air actually goes up or down. Because if it expands, it'll get cooler. And that means it won't go higher because it would kind of go down a little bit because it's expanding, getting cooler, but it's warm up there, so it won't go through that level. And if it sinks down, right, it's cooler down there, so it won't go that far because it's already warmer, so it won't sink anymore. So it stays right where it is. Okay, you get this temperature inversion. Well, this is what happens in Los Angeles because of smog, right? This is Los Angeles. Because you get this temperature inversion, you've got hot air from the desert coming over these little mountains outside of LA, nice and warm up here. Well, cool air coming off the ocean. Well, guess what? Cool, hot, the smog has nowhere to go, and it just sits there. And it's nasty.
You're driving in, like outside
Yeah.
LA, and you drive in through, you see like the cloud of like smog.
You can totally see it. And it's not moving up or down, is it?
Yeah.
It's very stable, but we don't really like that so much because it's smog and it's like bad stuff for your lungs. Yeah, not so good. Okay, let's fly through clouds. Again, no pun intended. We're going to go through clouds pretty quickly. 4 major types of clouds: high clouds, middle clouds, low clouds, and then clouds having vertical development, meaning clouds that aren't high, low, or mid. They're kind of like whoop all the way up this way. Okay? All right, we've got all these different words. Back when you're in like 4th grade, they make you memorize some of these things. I'm not going to make you memorize any of these, right? Just be able to kind of recognize them. Okay? A couple of these you should probably know. Cirrus clouds are the ones that are way up high. Okay, 6,000 meters. By the way, does anybody live in Montana? I forget. You grew up in Montana? What do they call Montana?
Big sky.
Big sky. Why do they call it big sky?
Because it looks massive.
Well, it looks massive. Part of the reason it looks massive is because it's got lots of cirrus clouds that are way up high. Makes the sky look just huge because the clouds are way, way, way up high. If you've ever been in like a house that has really high ceilings, it looks like there's a ton of space. And it's not necessarily as much space. It's just because the ceiling's higher. It's more volume, but not much more usable space, in that sense. But anyway, okay, high, middle, low, and then clouds that have vertical development. Let's go through a couple of these here. Let's see. Let me zoom in here. Got lots of cloud pictures we can probably show you too. So I'll just leave those there. Okay, cirrus clouds. I don't like this picture. I've never seen clouds that look quite like that, but they're kind of wispy. They're way up high. You've got cirrocumulus clouds, which are the ones that you can see little like pieces. You can see lots of sky coming kind of through, but there's lots of little pieces. Okay, cumulonimbus. Okay, these ones are generally storm clouds. They're vertically developed. When you see these guys coming, probably gonna be a thunderstorm. Okay, cumulus clouds, the lower ones. Cumulus ones are the ones that you generally think of like they look like teddy bears and things, right? Okay. All right. Stratocumulus. Okay. All right. By the way, is it nimbus? I think nimbus means like water producing or something. So if you see that, you're going to get you're going to get water. Okay.
Would that be Latin?
I'm not sure if it's Latin. Don't know what it is actually. Possible. Isn't that what was the name of Harry Potter's
Nimbus 2000.
Nimbus, there you go, Nimbus 2000. Did it make it rain? I don't know. I don't know. All right. So clouds, what causes clouds to develop? Well, clouds develop because you get more condensation than you get evaporation. Okay? Now, as air rises, remember it cools, and it ends up being saturated. Once it's saturated, it starts condensing out into this cloud. Now, do clouds float?
They're not saturated.
They're not saturated? What do you mean they're not saturated? Clouds are like 100% humidity. because they're water vapor. They're water vapor in the atmosphere. Now, the amount of weight of a cloud is like a 747. It's like a huge amount of weight. Okay? They are not really floating so much as falling but getting pushed up by other air. So the air has to keep pushing it up in order for the cloud not to kind of fall all the way down. Okay, so that's why a cloud is not, it's not really floating so much as constantly being pushed back up, if that makes any sense. They are pretty heavy. They are heavier than the air around them. Okay, clouds are. All right, let's see if we can get this. Which of the following clouds appear at the highest altitude? These little wispy ones? I think that's a much better picture than that silly diagram. Yep, cirrus. Okay, so how do we get rain or precipitation or whatever other kind of precipitation we have? Well, first thing, you need some dust, believe it or not. If you had pure like air with no dust in it, it would never rain, because each little raindrop is kind of surrounding a little piece of dust, as it turns out. Okay? You need updrafts, which are going to kind of push up into the clouds. You need stationary drops of water growing on these dust particles, and then you have the actual raindrops that fall. You need some vertical development. That's why those cumulonimbus clouds that are vertically developed are the ones you're generally going to get more rain from. Okay, because you not have to have these droplets like hitting each other. What happens is the one from the top kind of hits the one below it, and hits the one below it, and hits the one, and then they bounce out, and then finally the ones at the bottom don't have anybody to hit, and they pour out rain. Okay. All right. Raindrops actually shrink as they fall. So if you're way up high when the raindrop's actually forming, well, it's going through the air, and as it's going through the air, now it's not in this really densely saturated area. It's going down. Number one, it's falling, so it's got lots of air going past it. And number two, there's no, like this, it's not saturated, so it can actually evaporate more. So as the raindrop falls, it gets smaller and smaller. Okay? There's this term called verga, or virga, I don't know how to pronounce that, that is when raindrops actually come down and then they disappear before they hit the ground. So it could be raining up higher, but then by the time they hit the ground, all the water's gone, so it doesn't actually hit the ground.
Dust falling.
At that point, it's just dust falling. I guess so. That's kind of gross. Okay. All right. Air masses. Not going to spend much time on this. There's a whole bunch of different types of air masses. When you're watching the weather report on the news, they sometimes mention these. Okay. There's maritime Arctic, continental Arctic, maritime polar, continental polar, maritime tropical, or continental tropical. Okay. Places that we get a lot of this. Let's see. Mexico, southwestern United States, continental tropical. Okay. Let's see. By the way, on a map, these are the little symbols they'll use. Lowercase m, big A is maritime Arctic, etc. Okay. Characteristics, a whole bunch of different characteristics here. Not going to make you memorize those. Maybe I should.
Will we be in like two different
No, I
ones?
won't. Sorry?
Will we technically be in like two different ones?
You mean in the US? Yeah.
Wouldn't like the Northeast be continental polar?
Yeah, I would say the Northeast is either continental polar or maritime polar, depending on where you are, right? Or continental tropical, or maritime tropical if you're near the water there.
So this is when the two hit and we get big storms?
Ah, that's coming up. Yes, when the two hit, we do get big. Here we go. Yeah, continental polar up here, continental tropical down there. Kind of not really any right in the middle there, but okay. Lots of different ones. Okay. All right. Okay, so sometimes air lifts up. Okay. Atmospheric lifting. We've got convectional lifting. Convection as in just like convection we learned about like 15 chapters ago, right? You've got orographic lifting. I'll show you a picture of that in a minute. This is where you get a rain shadow where there's actually no rain, kind of like the Chinooks, I guess. But I don't think that's orographic lifting. And then you get frontal lifting where you get the clouds, the nice cirrus clouds actually turn into cumulonimbus clouds, and then it's about to rain. Frontal lifting. We'll get to that. OK. Here's a little example of convectional lifting. Well, the not really seeing what's going on here, but the wind is coming in, and kind of lifting these clouds up. And these clouds just, they look like they're floating by, but they're continuously being kind of pushed up, buffered up by the wind. Okay? All right. Okay, here's orographic lifting. Yep, this looks like the Chinook from before, right? Get the warm air rising, get the moisture, cool air depleted, and it sinks, rain, shadow. I don't know why they broke it into two different parts, 'cause it looks the same to me. Okay? And then finally, you can get a cold front. Okay, take a look at this. You've got cold air here coming this way. You've got warm air over here. Okay, and the cold air kind of comes through. Well, look what happens. You get wind kind of going up like this, and the warm air is rising up. And as the warm air rises up, it can't hold all that liquid anymore, and you get rain. And sometimes you get thunderstorms as well. Cold front comes in. Okay, so frontal lifting. We have frontal lifting with a cold front, and we also have, if we have a cold front, we can also have a warm front, right? Here's what happens to the warm front, right? If you have a warm front here, okay, the warm air comes across and just starts kind of gradually lifting over the cold air that's stationary there. Lifts, 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 and you get nice clouds, maybe a little bit of rain in here. But you get nice clouds up here, and then it's all very nice over here. Okay, so when a warm front's coming, you know it's probably going to be relatively good weather. When a cold front's coming, then not so good. Okay? All right, those are our fronts. Okay? And then you can get an occluded front, which is when a warm air or a warm front and a cold front both move in and smack into each other. Lots of rain, lots of yeah, kind of bad weather. Okay, if they say it's an occluded front, you're probably not flying that day. Right? Yeah. Okay. A cyclone. We're not quite into the violent weather yet, but a cyclone is just an area of low pressure where wind actually flows. Okay. We do have Coriolis effects here. Okay. Counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. Cyclones do form into things like hurricanes and well, cyclones, but we'll get to that in a little bit. And you do get air converging in the center, which is the lowest pressure. Keep that in mind. In the center, we've got the lowest pressure, and it goes upwards. Okay, we'll get to that in a minute too. Now we're into the violent weather. Okay, all right, storms, violent, rapid changes in weather. Okay, this is why I become a weather forecaster, so you can get into talking about storms, right? Work for the Weather Channel. 3 types of storms: thunderstorms, tornadoes, and hurricanes. Okay? Okay, who's here's been in a thunderstorm? I think we all have, right? Who's been in a tornado? No kidding, you've been in one? You've actually been in a tornado. Where?
In Oklahoma.
Oklahoma? Not Kansas? Oklahoma. Wow. All right. Andy, what are you? Mississippi. All right. I guess I'd like to see a tornado, but I don't really want to be in one. Yeah. How about a hurricane? Really been in a hurricane before? I've been in a hurricane. I've been in a couple. I've been in one in. Yeah, there was one in. I don't remember which one that was. 99? Yeah. 99. I don't know which one that was. Andrew? No. I don't know. I was in a hurricane, a couple of hurricanes in Florida. I was down there.
Was it 99, the one that hit Maryland really hard?
I don't remember. Where were you?
Jersey.
Jersey? Maybe it was. Yeah, maybe it was. Okay. Anyway, let's talk a little bit about those. So, thunderstorms. Humid air rises. Because it rises, it cools, condenses into a single cumulus cloud. Then you get some unstable moist air, also rises. Okay? And because of that, it rises through the thundercloud, or through the cloud started there, causes a thundercloud, and you get lots and lots of energy out of that. Okay?
Is that because it's brushing past
It's part of it's because it's brushing one of the reasons you get the static discharge or the static buildup is because of the things brushing past each other really fast. Lots of energy in a thunderstorm, and it has to do with this kind of unstable moist air that's really rushing up and down, or well, rushing up. Okay. All thunderstorms, well, thunder and lightning. Okay, you might not see the lightning, but there is some lightning there. This is kind of a silly thing. The electrical energy flowing from cloud to ground, lightning.
What?
As lightning heats up the air, we get thunder, right? That's what you get. That's why you get where you get the thunder. Okay.
From the ground to the cloud.
It depends. It can go both ways, I think, but it depends. I don't know which way it actually, the current actually flows. I think from air to the ground, but I'm not sure. Okay, tornado, funnel-shaped column of air. We've all seen a tornado. Low pressure cone that forms from a cumulonimbus cloud to the ground. Okay? Funnel cloud, kind of like a tornado, but it doesn't actually touch the ground. Okay? And tornadoes are really dangerous because there's a lot of energy there. Okay? I have one video of this. Let me show it to you. Let's see, that was hurricanes. Let's do the monster tornado. How's that sound? Okay. All right, you want to hit the lights? Thank you. Thank you. This is called Gone in Seconds or something like that? Destroyed in Seconds.
Storm chasers Reed, National Bishop, and their friends are trying to document as many funnel clouds as possible.
Joel, what do you think about this weather situation today? It's a little too close to home. You've got to be kidding me! We have a monster tornado! A monster!
Oh my gosh.
Wow, holy that's a house. Oh my god, oh no! Crap.
In between twister sightings, they're pummeled by hail. That's big enough to crack the windshield.
We're going to windshield! Look at those hailstones!
A house located behind some trees is buffeted like confetti.
Oh, that! Whoa, did you see that?
Oh, not good, not good. Oh my god, not good. This thing is intense.
As they enter the small town of Manchester, the group witnesses a massive tornado forming. It soon grows into a Category F4 storm. An F4 is extremely rare, accounting for about 1% of all recorded tornadoes.
There's the vortex!
Oh wow.
The vortex of an F4 produces winds in excess of 250 miles per hour.
This guy's getting big.
And this one's more than a half a mile wide.
This is going to be some of the best footage of all time.
In their excitement, the storm chasers have ventured too close to the giant twister.
We'll be okay, Alex. I can tell you right now, we're fine. Just look at the meteorological beauty.
We're okay. We're okay.
Go back. No, we can't.
The twister moves with tremendous speed, and there's no doubt it's time to get away.
Go back, go back, go back, go back, go back. Okay, get in the car! Get in the car! Move! Back the up! Back up! Back up! Keep going, keep going, keep going! Keep going! Seriously! Back up! It's coming back towards us!
This thing is intense. This is violent tornado, guys, on the ground. Oh my gosh. Oh my gosh. Please, I hope they're okay.
An F4 twister is powerful enough to rip a house clean off its foundation.
Oh my God, I hope they're okay! Please be okay! Please be okay!
This is one of only 3 houses in tiny Manchester, and now it's gone.
Guess that's it. Oh, it's gone. All right. You can leave the lights on for now. Leave the lights off. So let's get through a couple more things here. So, hurricanes, on the other hand, okay, greatest storms on Earth. Just ask some people in the south of the United States, right? Energy comes from latent heat from condensing water vapor. Now, if you ever noticed, when you're watching the Weather Channel and they show in the hurricane where it's coming from, right? In the Atlantic Ocean, like down near like Cuba and that whole like area down there, or I guess for you guys down here, right? And then it kind of sweeps across the United States. Well, it's because it's gaining all this energy from the water. It's sucking, it's like all that water, that warm water is going into the atmosphere and creating a lot of water that's going to end up dumping on wherever the hurricane ends up landing. Okay, so you get rising warm air, you get low pressure near the surface, drawing in more warm, moist air. The winds rotate around a central low pressure area. What do we call that? The eye of the storm. That low pressure area is the eye of the storm. Continuous supply of energy from tropical waters. If you've got water that's warm, you're going to be able to get more and more and get bigger and bigger and bigger. Okay, and notice once you don't get many hurricanes that hit Kansas, right? Because by the time they get there, there's no more like energy source. The warm water is just none up there, so not going to get that nice warm energy source. Okay. All right. Strong vertical wind shear can cause warm air to tilt inward and spiral, and that's what's causing the spiraling of the hurricane. If you get more intense storm, you can actually become a tropical storm, and then you get to a gale, and then finally get to a hurricane. 300 kilometers per hour. That's like 170 miles an hour or something like that winds. Okay. Let's watch one more video on that. Hurricanes.
When Chuck Norris goes down there to practice around how it kicks, right?
There you go.
Violent winds, driving rain, killer waves. These are the hallmarks of a hurricane. Also called cyclones or typhoons, hurricanes are giant storms prowling the world's tropical seas. An average hurricane releases as much energy in a day as the explosion of 500,000 small atomic bombs. Hurricanes form in the summer and fall when the sun heats vast stretches of tropical ocean to over 82 degrees. Warm, moist air rises over these hot spots, creating thunderstorms. Upper-level winds and surface winds then come together, forming a circular pattern of clouds known as a tropical depression. When the winds exceed 39 miles per hour, a tropical storm has developed. When the winds reach 74 miles per hour, a hurricane is officially born. Inside the storm, bands of rain up to 300 miles long meet in the eye wall, the most violent section. Here, winds of up to 200 miles per hour spiral upward. Within the center of the hurricane, downdrafts of dry air create a strangely calm area called the eye. Fully formed, a hurricane may stretch over 500 miles in diameter. That's a storm nearly the size of Texas and reach a height of 9 miles. Most of these storms spin out over the open sea, but in an average year, 2 or 3 will strike the mainland of North America. And when they do, the damage can be catastrophic. Most dangerous is the storm surge, a wall of water that sweeps across the coastline where a hurricane makes landfall. About 45,000 people were killed by hurricanes in the 20th century, including some 15,000 in the United States. Hurricanes are also costly in dollars. 1992's Hurricane Andrew was the most expensive natural disaster in U.S. history, causing more than $25 billion worth of damage. Scientists are searching for better ways to predict the path of a hurricane. Special planes called hurricane hunters fly directly into these monster storms and drop sensors to measure wind speed, temperature, and air pressure, providing vital clues to the hurricane's direction. New 3D models are also helping scientists understand this awesome force of nature and provide quicker and more accurate warnings to anyone unlucky enough to be caught in its path.
Okay, what's the eye of the hurricane?
Center. Area of low pressure.
Area of low pressure, of course. Okay. All right. Okay. So, weather forecasting, right? Which is what we've got some weather forecasters on camp here. Okay. You got to collect data from wherever you are, and in fact, a much greater area than where you are actually. Okay. Computers these days help a lot. When back in, like, let's say the 80s, you might only be able to have, you couldn't have these 10-day forecasts, right? You could have like 3 or 4 or 5-day forecasts total, right? Nowadays we get 10-day forecasts and it's actually somewhat accurate. I mean, it's not always perfect, but you can predict out the weather a fair amount, more than you might think. Accuracy, though, sometimes is very interesting. There's this other, anybody ever heard of chaos theory? Okay, it's a type of math that's, that kind of came about in the like 1950s, 60s, 70s. And what it says is that a tiny little change in an initial condition, or like, let's say right now, you look at all the different parameters for the what's happening right now, a tiny little change in any one of those can completely change the end result. Okay, we call this the butterfly effect, which you might have seen a movie called that at some point. But there's this this idea that as well, the butterfly effect goes as follows: a butterfly in Texas can flap its wings, and then like 2 years later, you can get a tornado in China, right? And it's because there's a tiny little effect can make a huge long-term effect down range. Okay, we call that the butterfly effect. There's actually a video. I'll put the video online. I don't want to show it to you right now. We'll do that. And then finally, weather forecasting is, well, lots of different stuff goes into it, and you got to learn all these symbols. And then you've seen them all on maps and so forth. But all these symbols, like, obviously mean various things, and they've got a whole bunch of ways of categorizing it. And they actually have these little, like, I don't even know what these are called. They look like little like notes, music notes or something. But each little part of that around there means something different. Okay, you can really dig into to doing that. Maybe we'll look at weather forecasting in next week's lab. We'll see. All right. So I'm actually going to let you go a little bit early. And we will see you next week for astronomy.